Hello, welcome to the second part of this 10th lecture on polymer wear in the series of lectures on tribology for the beginners. This lecture is on polymer wear, and as we discussed earlier, polymer wear is a fairly complex mechanism, and therefore a large number of parameters and phenomena have to be discussed. Therefore, we needed to split the lecture into two. In the first part, we have discussed the polymer characteristics and particularly the engineering polymer characteristics and how they wear and the wear mechanism. And we also tried to develop a tool for predicting the polymer wear. We discussed there that polymer wear involves mainly adhesion, abrasion, and fatigue. All these three mechanisms may not work together, but partly or sometimes they may work together. So we need to take care of all the three mechanisms. And in the first part, we discussed the adhesion and abrasion of polymer wear. Now, in this part, we'll be discussing mainly the fatigue wear and the effect of or the dependence of polymer wear, total polymer wear, including abrasion and fatigue, on different parameters like roughness, load, etc. So let's go to the main issue. Now, fatigue wear for polymers are usually seen for elastic polymer, highly elastic materials which rub against stiff and relatively smooth surfaces. Fatigue will be dominating under such circumstances. In such a case, a particle is detached after a repeated contact over a localized contact area, as seen in the figure below. When a hard spherical indenter moves along an elastic strip, the surface of the strip in front of the indenter is compressed, understandably, whereas behind the indenter, the surface is stressed. Thus, an alternating stress cycle is created. Here, we must remember that the tensile stress is the most dangerous and damaging for the rubbing materials, and therefore we should try to avoid it. And also, we know that the number of cycles for failure may be given by the following equation number 8, which gives n, the number of cycles for failure, is equal to K4 within bracket sigma naught divided by sigma t to the power t, where n is the number of cycles for failure, K4 is the proportionality constant, sigma naught is the tensile strength under uniaxial loading, that means the strength of the material, tensile strength of the material, and sigma t is the amplitude of the reversing stress, and t is the experimental constant. Now, fatigue is usually inversely proportional to this number of cycles, n, for failure. Kragelsky and Nepomnyashchi in 1965, the references are given in the next page, proposed that the fatigue wear volume V2 per unit sliding distance of a single asperity may be given by V2 equal to pi a squared by K4 equals sigma t by sigma naught to the power t. That is the 1 by n basically. And pi a squared delta, if you look at the figure, the right hand side is the wear volume, because A is the contact radius and delta is the deformation. Now, here the unknown quantity is sigma t, because that depends on many parameters, and Hamilton in 1983 showed that the contact zone subjected to both normal and tangential forces, maximum tensile stress would occur at the trailing edge of the slider. And this is given by sigma t equal to 3w by 2 pi a square within bracket mu by 8 within bracket 4 plus nu into pi plus 1 minus 2 nu by 3 bracket closed. This is equation number 20. Now, here small w is load for single asperity. So we need to replace sigma t in equation 9 by the expression in equation 20. So we do that, but before that, we also need to put an expression for mu, that is the coefficient of friction, which would be dependent on many factors, particularly the thermal factors. And these have been discussed earlier, and we present here again for different contact temperature and speed. If the contact temperature is less than the melting point and the speed is, or Becklet number, which represents the speed, is larger than 5, then mu, the coefficient of friction, is given by 1.97 zeta 1 K2 by root alpha a to the power 3 by 2, where zeta 1 equal to T by W root V. K2 is the thermal conductivity, alpha is the diffusivity, and A is the contact radius, as we discussed earlier, and V is the velocity. Similarly, 3 more equations are given for different contact temperature and speed. For example, if the contact temperature is less than the melting point and Becklet number less than 0.1, we have two more expressions. And similarly, for contact temperature larger than melting point and Becklet number larger than 5, we have 2 more expressions. And also, if the contact temperature is larger than melting point and Becklet number is less than 0.1, like the slow speed, we have 2 more expressions. And these are given in 21. So combining equation 19, 20, and 21, we get the fatigue by volume for a single contact or for single asperity contact. We can now find the total non-dimensional fatigue wear volume by summing up the wear due to all the elastically deformed asperity. Here, it is important to note we consider only the elastically deformed asperity because it is the elastically deformed asperity that are likely to contribute to fatigue wear. Plastically deformed asperity would contribute to abrasion. So, when we combine equation 19, 20, and 21 and integrate them, then we must do it between 0 and capital delta CA. Capital delta CA has been explained earlier to be the critical deformation which distinguishes between the elastically and plastically deformed asperities. So we take only the asperities which are elastically deformed. Here again, we use the non-dimensional scheme that we used earlier for abrasive wear component. And this is shown in the next page for convenience. Now, before we go to this, let us remind ourselves that we are looking at the contact between two rough surfaces. But here, what we do is we transfer the roughness of both the surfaces to one deformable surface shown in the below and one rigid and smooth surface, hatched one, loaded from the top. This makes it easy for our mathematical calculations. So here we have got a mean line for the rough surface shown by the dotted dashed dot line, and the height of any asperity is given by Z, and deformation delta as shown here, and small d is the distance between the flat surface or rigid surface and the mean line. And while integrating, we need to use a asperity distribution, asperity height distribution. And that we do by using Gaussian probability function given by sigmas phi z equal to n, capital N, which is the number of asperity per unit area, e to the power minus z square by 2 sigma square divided by sigma to the power root 2 pi. Now we integrate this, as we said earlier, between 0 and capital delta CA, and we use the following non-dimensional scheme, where Z, as shown in the figure, is equal to D plus delta. Therefore, dz equal to d delta. Capital delta C, which is the critical non-dimensional displacement, will be small delta c by sigma Small delta c is the actual displacement, actual critical displacement that distinguishes between the elastically and plastically deformed asperities. It is important to note here that we non-dimensionalize all the displacement by sigma. Sigma is the standard deviation of the asperity height distribution. Therefore, delta, capital delta Ca is equal to small delta Ca divided by sigma. Capital delta is equal to small delta by sigma. D capital D delta is equal to d small delta divided by sigma, and h is the height, which again is non-dimensionalized by sigma, and a is the contact radius, which was taken for the hemispherical asperity. But here for abrasion or for conical asperities, which we use for developing the model for polymer wear, A would be replaced by delta cot theta 1, and B, the volume, wear volume, is non-dimensionalized by V divided by capital N sigma to sigma cube. So these are the non-dimensional scheme we used. We also used a number of non-dimensional factors for simplifying the mathematical formulation, where we use 4 friction factors: capital F HT, capital F LT, capital F HTM, capital F LTM. Now here, H represents high speed. That means where Peclet number is larger than 5. And T, small t, represents contact temperature less than the melting point. And L, small l, represents low speed. That means Peclet number less than 0.1. And Tm represents temperature, contact temperature, equal to or larger than melting point. So these are the 4 expressions given earlier in our discussion, and we use these for convenience in our formulation. We also use 3 more non-dimensional factors, or indices rather. Adhesion index, which has been discussed earlier and which was first proposed by Fuller and Tabor, and we have modified this for our use in polymer wear, and there we define it as theta is equal to K3 sigma by gamma. K3 is the elasticity constant, sigma is the standard deviation, and gamma is the surface energy. Similarly, before that, adhesion index simply represents the ratio of the force required to deform a conical surface, conical asperity, to a depth of sigma to the force corresponding surface energy, surface forces rather. Similarly, we have got abrasion index, lambda, which was again modified from Johnson's adhesion index for plasticity, and it is given by H sigma by gamma. H is the hardness, sigma is the roughness for the surface that's being used, and gamma is the surface energy. Fracture parameter phi is given by gamma E divided by, within bracket, pi A sigma naught square. A is the contact radius and sigma naught is the tensile strength. So these three indices are used in the formulation for simplifying the methodology. And before we go ahead, it is important to remember that if adhesion index is larger than 3.2 in our case, the roughness effect or abrasion would dominate. Similarly, for abrasion index, if lambda exceeds 2, then roughness effect or the abrasion effect would dominate. And fracture parameter simply denotes the detachment of particles on the surface, which is typically a fracture situation. So obviously, if fracture parameter increases, we would expect larger wear. With this introduction, we go ahead with the rest of the formulation. Now, the equation for V2 bar, that means the non-dimensional fatigue wear for different speed and temperature conditions are complex and lengthy, and they are available in the paper by Roy Chaudhary and Chakravarti. Reference are given in the next page. But here we present only one equation for clarifying few important issues. We present here the equation for contact temperature less than melting point and Peclet number larger than 5, that means high speed. So this is a high speed, low temperature situation where total of fatigue wear V2 bar, non-dimensional fatigue wear, is given by equation 22. Now, this is a complex equation, and 3 more equations are available in the paper noted. Now, there are a few points to be noted here. Here, surface energy is taken into account using Johnson's equation given in Johnson's et al. Paper in 1976 with a hemispherical model, hemispherical asperity, given by W is the load equal to K3 a to the power a cube divided by capital R minus 6 pi gamma Ka cube to the power half. Now here K3 is the elasticity constant, A is the contact radius, contact radius, and capital R is the asperity radius. We must distinguish the two. And gamma is the surface energy. But here, as we mentioned earlier, we are using conical asperities. And for correcting the equation for that, we replace capital R by 0.1548 cot theta 1 and small a is equal to 8 cot theta 1 for correcting for conical indenter. We also may note in the equation 22 that theta by lambda seems to be an important parameter. This has been noted earlier in all the equations. Here, as we said earlier, theta is the adhesion index and lambda is the abrasion index. If we put the expressions for theta by lambda works out to be K3 by H, which is simply a ratio of elasticity to plasticity characteristics of the material. So theta by lambda is an important parameter, and we'll see how that affects our wear. And as we said earlier, that we integrate between 0 and capital delta CA to take care of only the asperities which are deformed elastically only. So with this, we find out all the total asperity wear volume for fatigue wear V2 bar and add up with the wear volume for abrasion V1 bar obtained in the previous lecture, and we add them up as shown in equation 23 to find out the total wear volume. Now we'll be plotting this total wear volume for different important parameters like roughness, load, and etc. But before doing this, we must choose some relevant properties. So we have chosen two sets of parameters. Parameters are non-dimensional load, W bar, given by small w. Small w is the load or single asperity, square root 2 pi divided by capital N, K3 sigma square. Theta, as we said, adhesion index, K3 sigma by gamma, lambda H sigma by gamma, and phi fracture parameter, gamma E divided by pi A sigma naught square. So we have chosen two sets of values. The first set of values, W5, W bar 5, theta 5, lambda 0.25, theta 0.25, and mu 0.25, refers to high adhesion and low abrasion and fatigue wear. Whereas the second set of values, W bar 10, theta 50, lambda 5, phi 5, mu 0.25, 0.75 refers to low adhesion and high abrasion and fatigue wear. Now, since in polymer wear, abrasion due to roughness is an important issue, we first plot the dimensional total wear load against the roughness. Normally, in such cases, non-dimensional loads are plotted, and that is why we have developed equation 23. But to show the effect, we'll first put the dimensional wear. And this will do using the first set of parameters, that is W5, theta 5, lambda 0.25, 5.25, and mu 0.25. And again, there are two plots we have made. One is for shown in A, high speed below melting point, HT, and in the second plot, it is high speed above melting point, HTM. Now, in both these plots, one thing is very clear is that at low roughness, the total wear is very small. It's probably not zero, but if the roughness is zero, it will be zero. But there are hypothetical cases. Low roughness, wear is small. And as the roughness increases, the total wear shoots up steeply. That is very much expected because roughness will dominate, and although fatigue wear will be very small, roughness, the abrasive wear will dominate and the total wear will increase. Now, if we look at the scales of the two plots, in the second plot, the scale of the second plot is such that we can see for VHTM, although the trend of the plot is same, the wear is slightly lower. That is simply because VHTM means above melting point. So above melting point means there will be a transfer layer on the rubbing surface. And this will modify the surface roughness, or rather smoothen the surface to some extent. And hence we would expect less abrasion. And that is shown in the figure. So these two figures are quite clear, and it demonstrates quite clearly that for small roughness, total wear for polymer is small, and at high roughness, it is fairly high. So that gives a very useful industrial tip not to use very rough surface which would be rubbing against polymer. Next, we go to two plots in the top of the figure, top of the slide, where we plot V1 by V2 against roughness. Now V1 by V2 is the ratio of abrasive to fatigue wear. And the first plot is for high speed below melting HT. And the second plot, low speed above melting. So here we can see in both cases, at low roughness, the ratio is very small. Again, not zero, but very small. And that is because at low roughness, surface is very smooth, and you'd expect very large fatigue wear. And fatigue B2 being in the denominator, we would expect the ratio to be very small. And as the roughness increases, V2 takes over and the ratio rises steeply. Figure A and B, if we look at the scales, we can see that the wear is probably slightly more, or it starts rising a little earlier. That may be because of the melting wear situation, and also because of the low speed. But the trend remains more or less same. And the figure below the slide, we show scanning electron microscope micrograph of a pin, of HDP pin, in a typical pin on this experiment. With the increase in roughness. Now, when the roughness is small, obviously we would expect fatigue wear, and this shows fatigue cracks. So the left-hand side micrograph is for fatigue wear. As the roughness rises, abrasion takes over, and we can see abrasive marks on the surface of the pin. So this is a clear transition from fatigue to abrasive wear with the rise in roughness. Next, we go to another variation of non-dimensional wear against non-dimensional load. Here again, we can take two cases. Case A is high speed below melting, and case B is low speed below melting also. In both the cases, total wear volume rises monotonically with the increase in normal load, non-dimensional load. This is expected very much. And this is true for both high speed below melting and low speed below melting. But if we look at the scale, we may see a small changes in the total wear volume for low speed below melting case. This again is expected because low speed we would expect no abrasive wear. And that would, and also would expect a little bit less fatigue wear also. And this would explain the low non-dimensional wear in the figure B. The two figures in this slide down below gives a non-dimensional wear against adhesion index. For two cases, high speed below melting and high speed below melting and low speed below melting. Now here we see that when adhesion index is formed, wear is large. And as it rises, wear falls and then starts rising. This is because at low adhesion index, adhesion is large and this is for the first set of parameters, so where adhesion is prominent, and we have got large adhesion or small adhesion index, quite expected. And as the adhesion index increases, the wear falls because adhesion falls. And then as the adhesion index increases, roughness or the abrasion takes over and it reaches a plateau and then starts rising. This is shown in the figure D, although this is for low speed, but the trend is quite clear that with a large increase in adhesion, index, the wear increases significantly. This again is because in this case, or large adhesion index, there is no adhesion and abrasion takes over and we have got large wear. Here probably high speed and low speed makes a small difference that is shown in the different scales given. So the effect of adhesion index on the total wear is shown in these two figures. Next we go to another two important parameters. First is the abrasion index, total wear against abrasion index. Now here, at a low abrasion index, adhesion is very large. And we can see very large adhesion when the abrasion index is very small. And then it falls. And as the abrasion index rises, abrasion should take over and the curve should rise. But there is one thing we should remember here, is that for adhesion to be large, the roughness given by sigma or standard deviation surface heights should be in the nanometric level. 10 to the power minus 9. And for most polymers, H by gamma is of the order of 10 to the 9. So if we look at lambda becomes 1. And for it to rise, very small changes in sigma is needed. For example, an abrasion index of 100 can be obtained by changing the nanometric roughness to 0.1 micron. So this small change in roughness probably does not affect the wear, and we see almost a straight line. This is true for both cases, although the second case should be in HTM roughness is reduced in more, and that is probably shown in the slight changes in the fall of the curve. But the main fact is that has low abrasion and the wear volume is very large. And as it rises to about 100, wear volume almost does not change. And that is because of the reason we discussed here. Then we come to the variation of non-dimensional wear against theta by lambda. We discussed this earlier, that theta by lambda is an important issue. And if we put the values, it comes down to K3 by H, which is a elastic constant by hardness. So for low theta by lambda, it has to be very low modulus and very hard surface, very hard material. And that is probably difficult to find out, but if we find, we'll find the wear is very small. And as we increase around 4, it reaches a peak, and then it falls due to the compromise between theta and lambda. So this is a very important result from the practical point of view. It probably tells us that we should avoid a theta by lambda zone between, say, 3 to 8. Before that is safe, and above that is also safe. This happens for high speed below melting and high speed and the low speed below melting. There's a small dip in the curve. So this also is a very important factor in discussing, choosing the polymer. This is for the second set of parameters where we expect the abrasion and fatigue to be large. So with the exception of theta by lambda zone of, say, 1 to 3 or 4, the rest of the zone is not useful because it will give us very large wear. So these two curves are of very practical importance for choosing the polymer and the polymer properties for industrial use. Then we go to the next plot. This is a plot of non-dimensional wear against fracture parameter. Now there are three plots for two sets of parameters. First curve is for high fatigue and abrasion and low adhesion, and the second plot is for high adhesion and low fatigue and abrasion. But in both the cases, it can be seen that wear rises monotonically with the increase in fracture parameter. That is understandable because fracture parameters indicates the detachment of particles. So obviously with the increase in detachment of particles, we would expect larger wear. But there are three plots in each graph. VTM is the third plot, and there in both cases, wear is very small. This is because when there is a melting point, when the temperature reaches melting point, the fracture property is of probably not much of use because their fracture is not a prominent phenomena to look into. So for VHT and VLT, we will expect an increasing wear with the increase in phi. So the conclusion is that we should try to keep the phi within reasonable limit, probably between below 10. Next, we go to comparison between experimental and theoretical plots. They are so close that it is difficult to distinguish. We have plotted for two sets of operating conditions. First one is for 20 Newton at 1.25 meter per second rubbing. Second is for 10 Newton and 0.4 meter per second. These results are for pin on disk experiments. Here in both cases, we see that the results, experimental and theoretical, fall within a narrow band. And we can probably conclude that they agree well, with the exception of PMA and HDP. PMA at low speed seems to be out of the way, and HDP at relatively high load seems to be out of the way. Now, these may be attributed to experimental conditions. The atmospheric conditions make much difference in real wear, and this obviously could not be taken into account in the theoretical formulations. So with these two exceptions, I think we can conclude that the experimental and the theoretical results match fairly well. Now we see what we can conclude from this. We can say that the model or the predictive tool and the results from the predictive tool and the experimental results are fairly close. Although the model includes as many parameters as possible analytically to take care of. However, few things could not be taken care of. For example, the atmospheric conditions. Maybe there is a scope for improving the model there. The wear equations here are given in two groups, abrasive and fatigue. In each group, they are given for different temperature and speed conditions. High speed, low temperature, high speed, high temperature, low speed, low temperature, low speed, high temperature. And we have seen how this affects the results. So the results only confirm that the adhesion dominates for low roughness ranges and abrasion at higher roughness. This is quite understandable, and it is seen in both in the model as well as in the experiments. With the increasing friction factor and fracture parameter, total wear increases monotonically. This again is expected. Although we cannot conclude that higher friction means higher wear, but in many cases, friction factor is responsible, or friction is responsible for high wear. There is a unique value of theta by lambda, which can be presented by E by H, where we can expect high wear and low wear. So this is of practical importance, and we can, as we discussed earlier, we can avoid those conditions and choose polymers so that they can wear less. So this is probably these are the conclusions from our model and experiment. And although there are many more factors can be considered, but this itself is quite useful. So we complete it here today, and we'll go for our next chapter, the next class.